Hi guys, welcome back to another video of me teaching. And today I have this question on the board for you guys. So why don't we just get into question? Well, before we get into the question, I'm first going to tell you about a question that I saw the other day. It was this question. To find the value of all of these signs multiplied together. Now, of course, this is doable, but isn't it easier just to find the general form and just to plug it in? Well, yes, that's what we're going to do today. So we're going to find this, which is actually also called the general form of this. Okay, so we first have to watch, and we always do this before any single video. So what you see in the sign is a k pi over n. Now what does that remind you of? Well, I've said this many times before, but the root of unity. But not just the root of unity, the angle of the root of unity. But you might be thinking, no, isn't it 2k pi over n? Well, that's actually an easy fix. We can just let theta to be 2k pi over n, and that is just theta over 2, right? Now, with all of this root of unity stuff, what does this also make you think of? Well, of course, the polynomial that gives you the root of unity. Or in other words, z to the n is equal to 1 because it is over n. And now, of course, we can write this as z to the n minus 1 is equal to 0. But I'm not going to write that. I'm actually just going to straight away factorize this using its two most popular ways. The first way is, of course, the typical one, where this is z to the n minus 1 to the n, and we just use that formula. So z minus 1, and then 1 plus z, plus all the way to z n minus 1. And this is n minus 1 because this is actually z to the power of 0. And also, the second way is we factorize it using its roots. So the first one, z minus 1, or z0 times z minus z1, all the way until z minus zn minus 1. And it's n minus 1 again, because this is actually z0. So of course, when z is not equal to 1, then we can just cancel this and this. So we see that this part is equal to that part. And that's actually what I'm going to do. So when z is not equal to 1, then we see that this part is equal to this part. And I'm actually just going to write this as the capital pi notation. So capital pi as k goes from 1 to n minus 1 of z minus zk. So now look, the capital pi is starting to look similar to that, but the inside is not even close. And also, for you high schoolers, this might sound a little off, but just power through, and I will tell you why this is doable after. So what I'm going to do is I'm just going to let z to be equal to 1. And then I'll plug it into this. So the left-hand side will just be n, because there are n ones added together, because 1 is z to the power of 0. And this is equal to capital pi, k equals 1, n minus 1, of 1 minus ck, right? So now I'll tell you why we can do this. It's because, now for you college students, you might actually already know this. So we see that these are both polynomials, right? So polynomials are all finite dimensional, but it can satisfy for infinitely many values of z. And of course, that includes 1. So that is why this is doable. Now, anyways, we see that this is getting closer to this, but the inside is still not even close to that. So I'll just rub things out and we'll do the next part after. Okay? So these are all of the important things that we need to know right now. So What I'm about to say, you might think, has no correlation with the problem, but trust me, there is. So, we know that this and this are real numbers, right? So, of course, their modulus is the same, right? So, modulus of this is equal to the modulus of n, and we don't need the modulus because n is always positive, right? Now, the modulus of a product is the same as the product of the modulus. So we can rewrite this as capital Pi, k equals 1 to n minus 1 of the modulus of 1 minus ck, and this is equal to n. Now, this will actually be a very important thing that we'll use later on. Okay, now if we first ignore this, then what I'll first draw is a unit circle, and that will help you visualize geometrically what 1 minus zk actually looks like. So I'll draw a circle and the coordinate plane. This is actually an Argand diagram, so it's not x and y axis, it's real and imaginary axis. So of course this is the 1. And if we just draw a line with an angle theta, then we can see that this is zk. Why? Because this is just equal to e to the I theta, which is 2k pi over n, and that is zk. I'm going to write this out. Okay, so what does 1 minus zk look like? Well, of course, it is just this vector heading toward 1. Okay, so now that we have this, why don't we try and find the modulus of 1 minus ck? Because we know that the product of the modulus is also n. So it wouldn't hurt to do that, right? So if we try and find the modulus of 1 minus ck, then this is equal to 1 minus zk is cosine theta plus I sine theta. And if we unpack, it will be 1 minus cosine theta minus I sine theta. So now this is equal to square root of the real part squared, 1 minus cosine theta squared, plus the imaginary part squared, negative sine theta squared. And now this is equal to square root 1 minus 2 cosine theta, if we unpack, plus cosine theta squared, and then plus sine theta squared. So now we see that this and this is 1. So this is equal to square root. 1 plus 1 is 2. 2 minus 2 cosine theta. Now you might think that we're stuck. But actually, no, we are not. Well, how can we still make this square rootable? Well, we can use the double angle formula for cosine theta. But which version? The 2 cosine squared minus 1 or the 1 minus 2 sine squared? Well, since that is sine of something, then it will just make sense to do the 1 minus 2 sine squared 1, right? So that's equal to square root 2 minus 2 times 1 minus 2 sine squared of theta over 2, since that is using the double angle formula. And also, this is equal to square root, if we unpack further, 2 minus 2 plus 4 sine squared theta over 2. And this is equal to square root 4 sine squared theta over 2. And this is equal to absolute value. So now this is not modulus, this is absolute value of 2 sine theta over 2. Now, we actually don't need the absolute value because for theta over 2, it is only the top half, not the bottom half. So it is always positive. So we actually don't need the absolute value. Great! So we know that the modulus of 1 minus ck is that. So if we just plug it into this, then we see that n is just equal to capital Pi, k equals 1 to n minus 1 of the modulus of 1 minus zk is just this 2 sine theta over 2. So we know that theta over 2 is, of course, just k pi over n. So I will replace that. And now, to find that, we just have to divide the 2. But how many 2's do we have to divide? Well, n minus 1 2's. So this is also equal to, or I can just do this. N is equal to 2 to the n minus 1 times capital pi, k goes from 1 to n minus 1 of sine k pi over n. And so the capital pi, k equals 1, n minus 1 of sine k pi over n is equal to n over 2 n minus 1. So this is the final answer of this very interesting question. And also for fun, if you want to plug in the values of n into this formula, you can do that. Then it'll just be, since n is 7, it'll be 7 over 2 to the power of 6, which is 7 over 64. And that is actually the real answer. So we know that this is completely true. So thank you guys so much for watching, and if you enjoyed my video and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.